Hello folks, my name is Dr. Zachariah Hildenbrand. I'm here with my colleague Dr. Kevin Shug, and we are the Collaborative Laboratories for Environmental Analysis and Remediation at the University of Texas at Arlington. We're coming to you from the Responsible Shale Energy Extraction Conference, which is a very unique event bringing together scientists, concerned citizens, operators, regulators, and technology companies to have an honest series of conversations about environmental stewardship in shale energy.
We'd really like to thank the support of the Cynthia and George Mitchell Foundation and Earth Day Texas for allowing us to put on this event. We believe that this content that we're going to be providing to those who haven't been able to attend is going to help answer and educate a lot of questions surrounding responsible shale energy extraction. So we hope you enjoy the content. It's really my pleasure to introduce our next speaker. He's a good friend of mine, coming all the way down here from Denton. We're running up against each other all the time at different conferences, and always talking about looking for ways to collaborate and work together. And so he's a card-carrying mass spectrometrist, and he's going to tell you a little bit about some technology that he's been working with the company to develop. And we were fortunate enough to have the opportunity to work with them and apply this in the field, looking at air emissions. So, Professor Guido Verbeck is professor of chemistry at the University of North Texas, where he's been there for, I'm guessing, 10 years, but I can't point to him to verify that. But he's been there a while, and I think this is a really great technology. I want to point out, and he'll mention this as well, but at the close of the session, he'll actually have a live demonstration of that technology out on the Esplanade on the way to the automotive building. So without further ado, Professor Verbeck.
Can you hear me? Oh, that's probably a good call. Yeah, there you go. Maybe put the mic down. How's that? Good, good? All right. Thank you very much, Kevin and Danny and Zach. It wouldn't be successful without them. Luckily, Philip and Zach, of course, the workhorses of this data that you're going to see out in the field, published this just recently. Actually got two really nice papers this last year, so it's very exciting work. But in the Earth-based separations, we've got the car. And the unit's changed. It's version 2.0. It's outside, so we'll show it to you. We'll demo it to you right after Dr. Santos has talked to, and I guess the close for Kevin. But we'd love for you guys to look at it and play with it, and I'll get to show you some really cool applications with it. The interesting thing for me is to build instrumentation so that it's portable, field portable specifically. And I always joke when I give this talk to the Department of Defense, I say, Department of Defense always wants me to red light and green light everything that I do, right? But on Star Trek, we know the only person that could successfully use the tricorder is Spock. Everybody else who goes down there with the tricorder is dead instantly, right? If you have a red shirt or you have a tricorder in your hand, you're dead. So they jokingly, in the Department of Defense, nobody wants to know how the instrument works. They just want it to tell them the answer. So we do that. How do we do this? How do we get this mass spec smaller and smaller? There's two ways. The world does it two ways. There's a bottom-up approach, where we take devices on MEMS and make them really small and bring them larger. And then there's a top-down. And our group is focused, I used to be focused on bottom-up. I'm a convert to top-down now. I like to keep functionality of the mass spec as much as I can as I'm starting to shrink it down, and as technology develops, reducing more and more. You know, it's like Steve Jobs when he dropped that iPhone in the glass of water and said there's plenty of room in there, right? So to make it smaller. So that's what we work on. We're working around in this technology specifically in membrane inlet mass spec. And what this means to the world is that I can do specific type of chemistry. I can look for a type of chemistry by tuning the membrane to that type of chemistry. In the case of aromatics, in PDMS, which is what we use as the membrane, is very, very good at looking at sequestering aromatic compounds. So we can use it to pre-concentrate in an atmosphere down to the part per trillion level. Now, normally the membrane inlets would work in about the part per billion level, but we've added a couple of years ago, we added a little wrinkle to that to make it get down to the part per trillion. But essentially the way it works is you'll see in the car, the air comes in from the car, it flows around this, there's a membrane in between. That membrane likes a specific type of chemistry, and that chemistry is allowed in and the rest is allowed out. So I can train it to look specifically at aromatics. We learned today about the B Texas and yesterday about the B Texas. So this specifically trained to look for the B Texas, but not bring in air and all the other constituents that we're not interested in, right? And so this is exactly what we do with our membrane. It's then got a filament. The filament then fragments and ionizes the compound so that we can get a very, very specific signature on the compound. Here's sort of a diagram of how that membrane looks. You've got the chemistry that's coming around. It gets in contact with the membrane, diffuses across the membrane into the vacuum system, and the chemistry is pre-concentrated. What we did to make it better was we took IR photodiodes. Now what that means is, in the Verizon Fios realm, these photodiodes have become cheap. I can use infrared photodiodes that are at 990, 1300 nanometers, 1100 nanometers, and they cost me 50 cents. As opposed to back in the day where these photodiodes would cost us, 50 bucks. Well, now I can take 3 of these photodiodes, train them on the membrane, and as I'm doing the analysis, do a specific heating of the membrane, which allows me to open up the membrane. I can custom what type of chemistry that I can do with those IR diodes and allow for a higher sensitivity of these B-Texas. And we got it down to the part per trillion level in a 7-second response time. So this is the other important thing. So a lot of times in this field work, you'll see that the GC is coupled to mass spec. That is no good at 70 miles an hour. You're driving at 70 miles an hour, you need to know what the chemistry is when you drove through it. You need to know it instantly. And there are a lot of examples, even in the Department of Defense, where you need to know the answer quickly. And a GC just won't allow you to do that. So here's my car. You'll see it out there. This is version 1.0, where we actually turned the car into a mass spec. Version 2.0 is we actually created the mass spec even smaller now. It's backpack portable. So now you can pop it into your car, any car, do the analysis, and then when you find your culprit, whatever the chemistry is that you're interested in, you pop it out and you turn that space into your lab, essentially. The mass spec is now field deployable, and I'll show you that. So here it is. We use an RGA, essentially. It's a residual gas analyzer. It's produced by the silicon manufacturing. Why do we do this? Because these things have to sit on silicon manufacturing for years without ever going down. Because 1 hour, TI takes down the silicon process for 1 hour. It costs Texas Instrument $1 million. So Inficon, which is the company that we do this with, has spent a lot of time in making their instrument so rugged, their mass spec so rugged, that it can run for years without incident. And so we needed something that we trusted. We use the Ford Fusion Energy. Us in Texas have no idea what this is because it has electric power, right? So if it's not diesel or, I jokingly say that, and I have a Jeep with 33s on it, but this car is incredible. Anybody who wants to learn how to drive an electric car should always start with the Ford Fusion Energy line. Why? Because it is all electric, all gas hybrid. Why? Because the stupid people who drive electric cars for the first time, like me, can drain the battery in 20 linear miles, and then I'm stuck on the side of the road. Now I have a gas engine that can actually get me home. This one also has a little green leaf, you'll see later, that as I'm driving the car, it tells me how well I'm doing, how well I'm braking, how well I'm accelerating, how well I'm running and functioning in the electrical car. But the best part for us is I can run it in all electric. Now why is that important? Well, I have a part per trillion sensitive detector, and I have a car that's emitting. That's not a good combination. In fact, it picks up the car's own emissions if I can't shut it off. So what I do is I take the gas engine that gets us out to the Eagle Ford area, and then I switch it over into electric mode, and I can run it 20 linear miles and get my data and then recharge it. Beautiful car. Here's a deep well injection site. This is the controversial no-frac Denton. It went viral, right? It went worldwide. In fact, a lot of New Yorkers, when I go up to New York, everybody wants to talk about no-frac Denton. This is the area. There's a very interesting thing about this area. There's a well site here. That well site's been there since 2003. The neighborhood has not. So, who's at fault for this? I don't know. Lots of people not communicating with each other. But the city planners said it was okay to build a neighborhood here. These are starter homes, $70,000 homes, and there's a well site there that's actually using bad chemistry in their fluids. You can see how it looks here. Here's the wind here. Here's us mapping it. You can actually see the effluent stream. We false color this based on the concentration. Zach showed this in his talk yesterday on the concentration level, and you can actually see the wind and the benzene concentrations in this area. And now there are even more houses around this well site. Cymene and cumene are really interesting. Cymene and cumene you can see from diesel burning. So normally when you're burning diesel generators, that's what you're also going to see mainly from oil and well sites, because you've got diesel generators pumping. You're also going to see that. So we need to be able to tell the difference between, is it coming from the well site? Is it coming from the diesel generator? Where is it coming from? We need to be able to, as good chemists, we need to tell. And we can tell. This thing will look at all of these compounds rapidly. This is downtown Dallas for B, Texas. You can actually see that the concentration goes up outside the main core area, and that's mainly because of traffic. Right? The traffic's actually lower in the main core area of the Dallas-Fort Worth area than it is in the interstate systems around here. This is Galena Park. So as we know that there's a benzene, there's thought that there's a benzene leak. There's a pipeline that runs right through the middle of this. One of my friends told me about that, so we immediately drove down there and mapped it. And you can actually see that effluent stream from down there. Now, that was the nice thing about having a Ford Fusion. Ford Fusion can go anywhere, right? So this part of Houston is not where my student was supposed to be, and the cop pulled him over and asked him, are you in the right area? And he told him about the experiment, and the cop was very receptive. So it was very nice. We were able to get this data in Galena Park. Of course, for other aromatics, this is PCP manufacturing. So just as a side note, we can do clandestine drug manufacturing, and we can do it from the public space. All of this is done in the public space. Why? Because your effluent stream will eventually cross a road. And when it crosses the road, I can capture that. So it's like a drug-sniffing dog. I don't have to go on your property. I do not have to affect your civil liberties. But if your chemistry crosses a public road, I got you. I can separate you, and I can do point of source. And that's our new technology. So I did this with these. I've got my Heisenberg in my group, right? He cooks for me. So these are our cooks. We can see all of these. This is my makeshift trailer park that we have at the University of North Texas, and that we can map. And we published in Analytical Chemistry last year. Great data. This was a movie I don't think will run, but it shows you kind of how it is, but I'm going to show you in the car later after this if you guys are interested in how we collect the data. Now, the biggest thing that's interesting to us and that we're finishing up this year is what we call earth-based separations. We don't have a GC, so how do we separate these heavy constituents, B Texas, from each other, right? We have this effluent stream, and we also want to know point of source. So can I drive by on a public road here, but have that be the point of source and still be able to determine exactly where that chemical effluent stream is coming from, which one it is? And the answer is yes, I can. So here's the car, or different ways of running through the chemical plume. So here's my chemical plume. My chemical plume has different bands. Why? Because benzene, toluene, and ethylbenzene, in those cases, do not have the same diffusional rates. They don't have the same volatility. They don't have the same collision cross-section in airspace. They have already built in earth-based separation constants. So as I'm driving into an effluent stream, I will drive to the lighter, more diffuse compound first, then the second, then the third, and so forth and so on. And then I'll start driving out of that. And so I can create a Gaussian model of driving into multiple streams, out of multiple streams, determine what that chemistry is, and then triangulate that back to the point of source based on wind speed, temperature, and all that other stuff that's going on. So here's an example of that. This is with a program that's by the EPA called Aloha. So we simulated these initially. And if this car is driving in the stream, and you can see that we'll get through each one of these things at a different time. The mass spec identifies the first chemical compound, and after that subtracts it out of the spectra from that point on. It recognizes that as the first compound, subtracts it out, and if new peaks grow in, it identifies that as compound number 2, subtracts those out, new 3, 4, so on and so forth. And so this whole time, it's actually creating a separation, what we call earth-based separations, in a 7-second response time. Now, it's not as great or high resolution is GC. But what do you expect at 70 miles an hour, right? So this is exactly what it would look like. So the compounds are increasing in concentration, and the program and the software tracks it. Or new compounds grow in, and the program keeps track of that. And so the idea is, in these cases here on this Aloha model, can I drive on this public space? This is my neighbor. I don't trust him. I think he's Breaking Bad. So I'm driving here on my public space past my house. I own this. I own that air. That air belongs to me, the rest of the public. Can I point of source that? And the answer is yes, I can. Right now, within 4% error. That to you guys is like 5 feet at a quarter mile. So it's pretty accurate. It's definitely coming from the type of house, so we drive through that specifically. So here's an example of us doing it, driving a public space and sourcing it. This is going to be published this year. So you guys are seeing it for the first time. We're introducing the world to earth-based separations because this is going to be a rapid determination technique. So here's one that's within the last tape. What we'd like to do is now more complicated environments. It's nice at Eagle Ford and in those areas. Why? Because it's flat, it's straight, it's easy for us to get 4% error in those areas. Not so good here in downtown Dallas, for instance, if we're looking for a chemical effluent stream. And so we're going to have to look at more complicated models, and we're going to be working on that this year.
Where was that location?
Oh, this is just a simulation for Los Alamos. This one here? Yes, ma'am. Yeah, nothing to be alarmed at. But it's really interesting based on airflow and turbulent flow, how you can have as much of a concentration at this point right here as you do from point of source in these types of turbulent areas. Interesting. So this is 2.0. So we took that whole instrument with my buddy Ken Wright at Infocon. We put it into a Pelican case. We reduced it down to 30 pounds. It's backpackable, and we took it down to Antarctica. Why? Part per trillion is impossible detection limit in the northern hemisphere. We see India's contribution, China's contribution, industrial nations' contribution to our air all the time here. So we put it in the backpack. And we took it down there to get a zero, and there's us at the top of Sierra Madera, which is the last island in Chile, right before it goes into the Antarctic volcanic stream. It's awesome. What a great trip. A lot of fun. We found zero on this island. You can see we got a lot of zeros. There's a Navy yard in this island, and so we can go down there to get our industrial footprint, no problem. Come out, get our zero. We had to actually, like our speaker before, we had to take the chemistry with us. So you take this pristine environment and then introduce xylenes and toluenes to it because we didn't know if our instrument was working. The ideas in the future are sort of putting these things on, you can put these things on a fence line to identify leaks within plants, specific leaks in plants, localize those. We're going to put these on robotics and with a switchgrass program to look at respiration of plant life through the different aromatic compounds. And these are the guys, I get to go up here and look good and take all the credit for this, but Philip's done all the work, Zach with Kevin Shug and his group, with Clear and all the work that they did down on the Eagle Ford that you saw earlier. Infocon, who's all in on this. This instrument is now a technical readiness level of about 7. They're ready to mass produce them, so it's a really, really cool instrument to have Infocon on. And Pfeiffer. As you can imagine, having a turbo pump, those of you who don't know anything about mass spec, having a turbo pump driving over dirt roads, not a good thing. Pfeiffer's done a really, really good job ruggedizing this instrument for us. So anyway, thank you guys for your time.
Thanks, Guido, very much. I mean, really, really cool technology. We do have a few questions, and they're, I think, kind of hinting at some of the same questions I have. And you said this is getting to a certain technical readiness level and to be mass produced. What's going to be kind of the marketing campaign? I mean, are we talking to law enforcement, or what about a community who has some concerns about an operation nearby? I mean, is it going to be affordable for them to be obtained?
Yeah, we talked about that initially with a company called Smart Talks. They're interested in that technology space for the law enforcement side. Right now, as a research price point, this instrument, it's a mass spec, so it's going to cost you about $80,000. Infocon's kind of promised that would come down to $50,000 and $40,000 in the future for mass spec. But you get a broad spectrum chemical sensor. So the idea was more floating the idea about creating a fleet of vehicles that are available for the whole of the community. And when the community needs one, they call one in as more of a leasing technology. I mean, because it would be a lot cheaper for the community. They certainly don't need it all the time. Maybe you just want to drive by it. You know, you can't profile, so let's talk about civil liberties. But for oil and gas applications, this is great. If people feel like that there's an effluent stream or they're smelling something funny or something's going wrong, it make it a cheaper price point for this to be a service. So we are looking at that service side of it, and then the other side of it, for the plant side of it, of course, they can afford it. So, yeah, I think for what we're talking about here, it would be much better to have a service type of oriented.
And do you have any communities you've already kind of reached out to, or that you?
Yeah, and so New York is really excited. We heard about it before. Infocon is in Syracuse. So one of the things that was great about New York, when they stopped their shale production, they're going to turn it back on. I mean, they're going to get after their natural resources. That's what we do. Infocon's now perfectly poised to create this for the New York State applications. As these turn on or as these small pilot programs start to go, they can roll this instrument out with it. Yeah.
Great, Guido. Thanks very much for spending the time and telling us about this.
Come and see it at 12, 13, 40. Yeah.